Hey there, let's take a look at how to find derivatives of exponential functions. And then we can look at the antiderivative as well. So if you have a function y equals 2 to the x, it's exponential because the variable's in the exponent. And if you're asked to find the derivative of that, you might think that, okay, well, I'll try the power rule. But if you do that, if we look at the power rule here, if I do that, if I find y prime by doing the power rule, bring that x down in front, and then it's 2, and you subtract 1 from the exponent. Well, let's see if this actually works. So let's look at the derivative. If we wanted to find, let's say, y prime of 2. No, let's not use 2 because I have 2 to the x. I want to use a different number. Let's say 3. So then the slope of the tangent line at y prime equals 3, if I put it into this function, it should equal the numerical approximation of it. So in my calculator, I put y1 equals 2 to the x, and I am going to graph that along with its derivative. And if you haven't done this before, you follow along with me. Click on the math button, and we're going to find the derivative, and we're going to graph it. And that derivative we're going to get from n derivative, and the n, oops, I need to punch the number in. The n stands for numerical derivative. So what it's going to do is it's going to take 2 to the x, and it's going to find, so your graph of 2 to the x looks something like this. And we're going to find the slope at 3, which probably, this is not to scale, but we're going to find the slope of the tangent line. Can't even draw it, it's so steep. So when x is 3, we're at 3, 8. The slope at that point is going to be pretty steep, but what your calculator is actually doing is it's going to go, it's going to find a symmetric difference quotient. It's going to take a point like 0.01 units to the left of that 2, 8, and it's going to go to the other side, and it's going to calculate the slope between those 2 points. Because your calculator is not smart enough to do calculus, it has to estimate the slope like we did at the very beginning of the year when we let those points get closer and closer to each other until you find the instantaneous rate of change, which is the derivative. So back to this, if you go back again, it's math, and then you're going to go to number 8, and the derivative, to put that into the calculator and have the calculator graph the derivative, we want to find the derivative with, it's flashing here, we're going to put an x because we want to find the derivative with respect to the variable x, and then we want to, we could type in the function here, that's what it's waiting for me to do now, and I could just type in 2 to the x, which would be easy to do, but because it's such a short function. But if it's a longer function, you're going to want to know this process. If I go to vars, which is next to the clear button, or stands for variables, and I go over to y variables and hit enter, and again, if you're having any trouble following along, you can pause and go back, but you can also look at my keystrokes here. They are all showing up at the bottom there. And I'm going to take and hit, I want y1, so now this calculator is going to find the derivative of y1, and again, it's calculating little tiny slopes at each point. It's going a little bit above, a little bit below, and finding the slope and then graphing that slope. And it does this over and over and over, so you'll see that this is going to graph kind of slowly. And we want to estimate the slope using a numerical derivative at x equals 3. So I'm going to set my window, and I could go from like 0 to, maybe I'll go to 5. And then, and I just know, so let's see. So negative, if I go -5, but I want to go up higher in the y direction. I'm going to go to like 25. If I push graph, that is the graph of 2 to the x, and that is the graph of the slopes of 2 to the x. And notice it's very similar. The graphs look very similar. But the red graph is the derivative, an estimate of the derivative. So if I push trace and I find what the derivative's value is at 3, Right now I'm on the blue graph, as you can see, which is our 2 to the x. And so I'm going to push the down arrow to get to the red graph, and then push in 3. And now what the calculator is going to do is it's giving me, because this was the graph of the derivative, at x equals 3, you should get something like 5.54 or 5.55. So let's see if that happens when we put 3 into this function. And if it's not approximately 5.55, we've got a problem. So the function is going to be 5.55 times 2 to the, so we're just putting 5.55 in for both of those x's. So let's try that. Let's see what happens here. So 5.55 times 2 to the power of, it's got a x minus 5.55, or x minus 5.55 minus 1, I mean. So I'm going to put that in 5.55, so I'm putting that in for x minus 1, and I get 130. Nowhere near the correct answer. So the power rule, long story short, does not work for exponential functions. So what you need to do, write this down. What we're going to do, we're going to it's going to involve logarithms. Okay, so here's how we're going to deal with this. We're going to take the log of both sides. Remember, when we're solving for an exponent, it deals with logarithms. So we're in, if I take the log of both sides, let's do the natural log of both sides. If I do natural log of y equals the natural log of 2 to the x, it allows me to bring that exponent down in front. So I have the natural log of y equals x times the natural log of 2. And remember, the natural log of 2 is just a number. Your calculator can evaluate it easily because we have the ln button and we have the log button. Log is base 10, ln is the natural log, base e. So ln of 2, we can just figure that out in the calculator. So that's a plus. Okay, so anyway, so now we have constant times x on that side. And on the left side, we have ln of y. So now what we're going to do, so take the natural log of both sides. Now we're going to find the derivative. So we're going to differentiate both sides. All right, so the derivative of y, of ln of y with respect to x, we're going to have to use implicit differentiation. You're going to have 1 over y, because that's the derivative of ln of an argument. 1 over the argument times the derivative of the argument, which is going to be y prime, because we don't know what y is in terms of x. And then on the other side, we have x times ln of 2, which means we have a constant times x. And remember, if you have a constant, we can leave the constant and multiply by the derivative of x, which is just 1. So it's just ln of 2. So that, again, ln of 2 means e to what power equals 2. So that number, ln of 2, is going to be something a little bit less than 1, because e to the first would be e, which is roughly 2.72. Hopefully you remember that. So 2.72 to what power equals 2 is what we're finding when we're finding ln of 2. This is going to be less than 1. So now I'm going to solve this for y prime by multiplying both sides by y. So I get y times ln of 2. And we're done, but we can actually get the derivative in terms of x. Right now it's in terms of y. We can get the derivative in terms of x because we know that y is equal to 2 to the x. So y prime, for the function 2 to the x, y prime is equal to 2 to the x, because I'm substituting 2 to the x in for y, times ln of 2. So that is the general form of the of exponential functions. And exponential functions, the base has to be positive and it cannot equal 1 because that would make it not exponential because it just 1 to any power is just 1. Okay, so this should go in your notes. If you have a function f of x equals b to the x, then the derivative is going to be b to the x. So this can be any base, as long as it's positive and not equal to 1. The derivative is going to be b to the x times ln of b. So for example, just a quick example here, if f of x equals 5 to the x, well, the b is 5, so then it implies f prime of x will equal, following this, it's going to stay 5 to the x, so instead of b I'm going to have 5 times ln of 5. All right, so all the other rules apply, the product rule, the quotient rule, chain rule, etc. So if we have a function f of x equals x squared times 5 to the x, then we'd have to use the product rule. And the product rule, recall, is u prime v plus uv prime. U in this case is, we'll say x squared. It doesn't matter which factor you pick. U prime is 2 to the x. V will be 5 to the x. V prime is going to be 5 to the x times ln of 5. So plugging that in, I'm going to have u prime v plus u, which is x squared, times v prime, which is 5 to the x, times ln of 5. And that would be your derivative. Let's do one more here. If we have y equals e to the x, we're going to find the derivative, which our base here is e, so it's going to be e to the x times ln of e. But ln of e, what is that? Think to yourself, what is that? The base is e, and so this is asking e to what power, or it's finding e to what power equals e. So e to something equals e. Well, that something would have to be 1, because e to the first would equal e. So ln of e is 1. So this is kind of a surprising thing. The derivative of e to the x is e to the x. It's itself, which implies that if you have a function f of x equals e to the x, if I find the slope at any point, so if I pick a point right here, the slope of this function is going to be equal to the value of that function. So this point up here is 1 comma e. When I put a 1 in for, if I find f of 1, I get e to the 1, which is e. So the point e, 1e is on the graph. So if I find the slope at 1 comma e, it's simply going to be e. The slope at that point, yeah, let me see if I can, the slope at that point is going to be exactly the value at that point, which is a very interesting thing about the function e to the x. And so all of this implies that because the derivative of e to the x equals e to the x, then the antiderivative of e to the x equals e to the x. I want you guys to write that in your notes, and then we're going to do one quick example here. Okay, so we're going to find the antiderivative of x squared times e to the x cubed. So we don't have a product rule that we can use, so what we're going to do is use substitution. We're going to let u equal the exponent x cubed, because I'm looking ahead, I'm looking for this pattern. If I take du, if I find du, I get 3x squared dx, and I have an x squared dx, I need a 3. I can put a 3 here, which means I need a 1/3 out here. So then this becomes 1/3, and then I'm going to rearrange this a little bit. I have e to the x cubed times 3x squared dx, and then that can be, I can use u substitution here, and I have 1/3 e to the u du, because this is my du, and then I get 1/3, the antiderivative of e to the u is e to the u. I'm going to sub back in my what I have for u, which is going to be 1/3 e to the power of u, which is x cubed, plus c. So there you go. Okay, I want you to try to do this problem on your own and then come back and check your work. You should get -1/3 e to the -3t. If you didn't, bring your question.